I want to thank Robert and Dave for inviting me here. Does anyone not have the handout? Okay, I'm going to... And there's more handouts in the back as well. So keep your hand up, and the handouts will come to you. So I'm going to split my talk into two of the three things I'm interested in. Biochemistry being one of them. Unfortunately, physics and cosmology is not one of them, so you won't hear about that. But today I'm going to talk about general science and the scientific method and some of the pitfalls in the scientific method. And then for the second half, I'm going to talk about Irish history, culture, and political revolution. I'm going to split the talks unevenly, though, because we have so much to sing and talk about. So I'm going to try and end around 11:15, if that's OK. And then we'll take a 5-minute break, and we'll set up for the Irish part. So wishful sciencing. When I decided to, when I arranged with Robert to give this part of the talk, just a couple weeks afterwards, there was a book review in the Journal of Chemical Education on a book called The Lost Elements, the Periodic Table's Shadow Side. So most of you know that the periodic table was one of the big gems of the scientific method. Starting in the late 1700s, French and German chemists started discovering elements like oxygen and hydrogen and iron. And they kept discovering new elements until 1869. Well, not until, but in 1869, the Russian chemist Mendeleev figured out this fantastic organizational structure for all of these new elements that had been discovered called the periodic table. And all of the elements that were discovered since then were plugged nicely into the periodic table. So it was this grand structure that explained many things successfully, unlike apparently dark energy, which may be retracted. But so the periodic table has been a very powerful example of the scientific method. And that's what we learn in school. Well, this book, The Periodic Table's Shadow Side, tells you about some of the things you didn't learn in school, which are the failures, people who set out to discover new elements and did not, or worse yet, people who set out to discover new elements, thought they had, named them, and then found that what they had was either an already discovered element or an impure version of an already discovered element, etc. So that's the shadow side of the periodic table. And we're going to talk about the shadow side of the scientific method, partly from my own personal experience as a young chemist and professor here at Willamette. So Pride and Prejudice in the Scientific Method. I'm going to start with a couple of quotes from that book review that I mentioned. And Jeffrey Kovacs, who wrote this book, talked about the wishful thinking that's sometimes involved, failures and missteps that happen along with the successes. And then basically the main point that I'm going to make here are these preconceptions that influence the interpretation of data. So when we think about scientific progress, now don't ask me how I quantified scientific progress on the y-axis, but I think it's qualitatively accurate that there's a little peak around minus 500, minus 400 when the Greeks reached the flowering of their culture. And then the Greeks were overtaken by the Romans, who were not all that interested in science. And interestingly enough, we think about Islam, modern Islam, a very different beast from Islam during the flowering of the Islamic Empire. The flowering during that time period from about 800 to about 1100, Islam was a very liberal religion, very interested especially in astronomy, also in health. So Galen, one of the key figures of that prefigured modern health, got almost all of his best ideas from Muslim physicians back in the year, around the year 1000 plus or minus 200. The Muslims were defeated, the Middle Ages followed, and the Catholics were for sure not interested in liberal science, as evidenced by what they did to Galileo. But you can see around the year 1700, 1750, we see this steep increase. So what do you think is responsible for that steep increase in scientific progress? What's that? The Presbyterians. As far as I know, there is no wrong answer, but as far as I know, that might be one. Somebody said here the Industrial Revolution, and that's partly true, but actually the Industrial Revolution is more or less a result of this other thing we're going to talk about, which is in the title of my talk, the scientific method. Yeah, so scientists used to be called natural philosophers, which, like, for example, the atom, Democritus proposed the idea of the atom, not because he had any evidence, obviously. He lived in the year minus 400, I think. Just because he thought it would be a really cool idea if there was an indivisible particle of matter. And he turned out to be right, but science was done up until the scientific method by coming up with really cool ideas that sometimes were right and sometimes were wrong. But the idea of the scientific method is your really cool idea has to be based on some data, and then it has to be supported or disproved with some data. So the importance of the scientific method is uncontested. So let's talk about the scientific method. All right, you all have probably seen some version of this in grade school or in college. You start by defining the problem, then you make observations, you find a mathematical law that relates your observations, you propose a hypothesis that explains the law, you do more experiments, and if your hypothesis is fully tested over and over and over again and never disproved, eventually, if you're lucky, your hypothesis becomes a theory. And believe me, there aren't that many theories in science. Theories usually result in Nobel Prizes. So one of the important take-home lessons you need to take from this part of my talk is that you need to distinguish, as is often the case, science is full of jargon, but a lot of science-y words, truthy words, actually have parallels in modern parlance, but they're not the same thing. When we use the word theory in modern parlance, we're really talking about hypothesis, right? I have a theory that this is true. A scientist would never say that, right? Gravitation is a theory. Evolution is a theory. These are things that are well proven and have been awarded the Nobel Prize. If you're just guessing about something, in modern parlance we call it a theory, but you're really talking about a hypothesis. So it's important to know the difference. So let's talk about some of these things. Defining a problem, very important. If I'm interested in whether God exists, or whether human souls can be resurrected, or whether voters can be persuaded by empty magical promises, these are very important problems, but they're not amenable to scientific experimentation. So you cannot define your problem. Your problem, as you define it, has to be testable. All right? So let's say I'm interested in depression, right? The phenomenon of depression in humans. And by the way, animals can get depressed as well, but most of our studies obviously are on humans because they can talk and they can tell us that they're happy or depressed. So there are two ways of going about that. You can go the holistic route, where you study a whole organism, a whole human being, and that would be called psychology. And there's also a reductionist route, which chemists and biologists generally take, where you would study depression in a single neuron, or maybe a network of 10 or 20 or 100 neurons. So there are two ways to go about it. We ultimately want to understand the same thing. Why do I feel depressed today or the day after the election? But there are two ways to go about it. You can take the reductionist route, study a single neuron, a bunch of neurons, and then eventually understand the brain and eventually understand the whole organism. Or there's a whole different kind of test you can take holistically as a psychologist, but you're still aiming at the same problem and you're still collecting data. Okay, so we want to make observations. So let's say you want to understand how much pain is involved when I'm throwing a ball at you, right? That's my problem that I've defined. Of course, this problem was already solved a few hundred years ago, but let's forget about that for the minute. So I'm up here and I've got a bunch of different balls, and you're standing there and I'm throwing these balls at you, and you're telling me on a scale of 1 to 10 how painful it is, all right? And I've got a clipboard and I'm taking the data. You're saying my pain after that ball hit me was 4.5, and the next ball is an 8, etc. So now I've got this set of data, and I want to define a law. And a law is a mathematical equation that explains the relationship between my independent variable, all right, you can see I abbreviate, and my dependent variable. The independent variable is controlled by the scientist, the experimenter, right? And obviously, I'm throwing the balls. I'm the scientist. So the independent variable is the thing that I control. The dependent variable is your pain, because your pain is going to depend on actually two things. What two things? Let's assume that let's assume I'm a really good pitcher and it's always going to hit in the same spot. How hard? Now, what do you mean by how hard? Let's be more specific. The velocity, right? Velocity of the ball and the mass. Good, and the mass of the ball. So the faster the ball is going, the more it's going to hurt. The heavier the ball is, the more it's going to hurt, right? So I'm going to have an equation that says pain equals some constant that I'll call k times velocity plus some constant that I'll call k prime times mass. All right? So these are my what variables? Velocity and mass. Those are my dependent variables because they depend on, I got it wrong. Those are my independent variables because I control them, and the pain is the dependent variable because it depends on velocity and mass. So now my experiment is done, right? I got beautiful data. I have a linear relationship between pain and speed and between pain and mass, and I'm all finished. No. Now I have to develop no, look at the chart. Now I went from 1 to 2 to 3. I have to develop a hypothesis, which is sometimes called a working hypothesis. Yeah, that's right, but there's something in between speed, mass, and pain. And this is what my hypothesis is. What's between there? No? What do mass and speed control in physics? Yeah, give me another word that has energy in it. Well, I'll give you a hint. There's two kinds of energy. Well, there's a lot of kinds, but in this, kinetic energy, right? So the more mass and speed the ball has, the more kinetic energy it has. The more kinetic energy it hits me with, the more force is impelled to my body, and the more blacker and bluer my bruise is, right? So we've got this law, which my hypothesis brings in some form of physics, energy, and then it's going to hit my biological tissue, and it's going to stimulate my nerves, which I have mechanotransducer nerves. Basically, they're the same nerves that tell me that right now I'm rubbing the little hairs in my arm. They're sensitive to touch, but of course they're also sensitive to really hard force as well, right? So I've got my data set, my law, then I've got a hypothesis that involves energy, biology, and then this response in my brain, which is pain mixed with fear and all the other stuff. Yeah. Okay? So now I've got my working hypothesis. Now I need to do more experiments. I need to study kinetic energy a little bit. I need to do more experiments. I need to study these mechanotransducers. I need to study tissue bruising and all that stuff. And of course, like I said, this experiment was done, hundreds of years ago. So we already know this. No one has disproven my hypothesis. I now have a beautiful theory. I know that kinetic energy exists. I know that I have nerves that are mechanotransducers. And I know that I have biological tissue that bruises. OK. So let's do, actually, you know what? I had another experiment I was going to talk about, but I think I'll skip that. OK, I won't. Well, I want to get to the Irish music, but anyway. Now you can see. All right, so this is an experiment that, actually, hold on just a second. Okay, so a couple of things that we need to be concerned with, as I mentioned, are the difference between theory and hypothesis, where hypothesis is tentative, theory is already proven, or as scientists say, never disproven, because you can never really prove something. Someday I could wake up, let this go, and it could float up. right? And then I will have disproven the theory of gravity. And I will get a Nobel Prize and Newton will lose his, right? But until that happens, it's still a theory. So you can never really prove a theory. You can only disprove it. But if no one's ever disproved it after hundreds of times trying, then it's pretty well accepted. So theory versus law, that's another thing that people get confused about, right? A law is really cool. It's mathematical. You can plot it, right? X-axis, Y-axis. You can even make three-dimensional graphs. But you're not done there, right? Newton finished there, right? Newton was working in 1666 when he proposed the force of gravity. The force of gravity between two objects depended on what? The masses of the two objects as well as the distance between them, right? But he wasn't equipped to be able to understand why do two masses attract each other, dependent on distance, right? 1666. Do you know who actually figured that out, came up with the theory, and won the Nobel Prize for it? Einstein in 1915, right? General relativity. So what is that? I don't know, 250 years went by between the law and the theory, or the hypothesis. So sometimes those two things are separated. If all you can do is do simple experiments, go ahead and do them, get your law, and then you may have to wait a few hundred years until someone has a good enough apparatus or a big enough brain. Really, Einstein, it was just his brain. Weird. I mean, who would have thought? Einstein woke up one day and said, if I have a ruler that's on a train or a clock that's on a train and the train's traveling, is the ruler still 12 inches if the train's going really fast? I mean, how many of us would have woken up and said, I think the ruler's not going to be 12 inches, you know? And, you know, Einstein set out to prove it one way or another, and he realized that you've got, you know, that the speed affects distance and it expects time. The clock doesn't run at the same rate on the moving train either. Anyway, I'm a little off the subject. So we've got theory versus hypothesis, theory versus law, and also this really tricky one, theory versus fact, right? So here's something about fact. In fact, it has proven by repeated experiments to be true, right? That drumming brings the sun back, right? So, because it works every time, right? So what experiment did they not do? Not beat the drum. Okay, now you're living in Africa. You don't know anything about science. Your sun is gone. Are you going to take the chance of not beating the drum? No. Einstein would, Galileo would, but you're probably not going to do that. So they didn't do the right experiment. But what I'm trying to get at here is fact is a very tricky object, right? If you listen to Rush Limbaugh, your set of facts, quote unquote, is going to be very different than if you listen to Gwen Ifill, God rest her soul, right, or PBS. So a fact can be something simple, right, like I can take a light intensity meter and I can measure the intensity of that light and I can get a reading on my meter, and that's a fact, and nobody's going to really contest that, assuming that I've calibrated my meter correctly. A lot of people want to say evolution is a fact. So here's the thing about that. The more complex the problem you're dealing with, the more tricky it is to call it a fact. It's easy to call something simple like light intensity or the darkness of or color, for example. But when you get to something complicated, to call it a fact, especially if you haven't done the right experiment, can be pretty tricky. So here's this other, I'll give you two other experiments. So a long time ago, I visited a friend of mine on a farm, and his neighbor had cows, and they had an electrified fence. This was in Wisconsin because he wanted to teach the cows not to wander. So he would start out in the spring when the cows first got out in the pasture. Let's call this April. That's spring in Wisconsin. And then he had the voltage on the fence of 25 volts. And he noticed he had his little clipboard, and he noticed that whenever a cow hit the fence, the cow would kind of jump up in the air. And let's say the cow jumped 1 foot. Oh, actually, you know what? I did this backwards because cows learn. So you start high voltage, but then as they learn a little bit, you bring the voltage down, and sorry, got my data backwards as well. Don't jump as high. In June, you bring the voltage down. Don't jump as high. And then in July, the cows have learned now, so there's no voltage, and obviously they probably won't even hit the fence because they've learned now. But if they did, they would jump 0, right? So I've got a set of observations here, right? And I can devise a law from this plot, right? Jump height goes up to 3. Fence voltage goes up to 75. So I've got 50 and 25. And I've got points, right? Obviously, this experiment didn't happen, but it could have. So I can devise a mathematical law from this relationship, right? Jump height equals voltage what? So when the voltage is 75, the jump height is 3 feet. So it's voltage divided by 25. And that's my mathematical law. All right? Right? And my independent variable, the one that I control, is what? Voltage. And my dependent variable is jump height. Right? But now I know the scientific method, so I'm not done. I need to devise a hypothesis, right? So my hypothesis says that voltage causes a jump. How? Okay. How do you know you're in pain? Your nerves, okay? So part of this hypothesis says that there's a relationship between voltage and nerves. In other words, how do nerves communicate? By voltage, right? And so if I give external voltage, that's a nerve signal. And the nerve will interpret that and cause what to happen? Muscles contract, right? And again, this experiment was done by Galvani and others back in the mid-1800s, I want to say, 1840, 1850, 1860. So we know this, right? So here's my hypothesis, that nerves are influenced by voltage. Nerves cause muscles to contract, and contracting muscles cause you to jump, right? So we have a beautiful hypothesis, and it's now been well proven. All right, great. Triumph of the scientific method. Well, back in those days, scientists also did nasty experiments sometimes, right? This is not a real nasty experiment, although I suppose it could have been. So you've got your experimenter, and she's decided, she's trained frogs to jump at her command, and she wants to know how important legs are. All right? So she's got the frog, she's got a yardstick, it's on a table. She says jump, and the frog jumps 12 feet. And then she cuts off the front feet of the frog, and she says, this is just a joke now. She says jump, and the frog jumps 4 feet. And then she cuts off the back feet, and she says jump, and the frog doesn't move. And then she's done her experiment, and she draws her conclusion, no feet, frog deaf. So the scientific experiment depends on setting up your experiment well, but also interpreting your data correctly, right? And you can't always do that. If, for example, if you're not studying the hearing of the frog, it's easy to draw a false conclusion about that. So there's all kinds of pitfalls in the scientific method, and we're going to talk about this one called wishful thinking. Okay, so all right, so the experiment I'm going to tell you about was an experiment I did back in the 90s with 3 different students, one at a time. And we wanted to study the effect of acid on frog skin. All right? Effect of pH on frog skin. So someone tell me why the brilliant young Professor Silverstein decided to impose this experiment on his vulnerable students. What's that? Yeah. Why do we want to, why did I and my students want to study the effect of acidity on frogs? Okay, exactly. So back then and now, to a somewhat lesser extent, acid rain was an important problem. And also back then and more so now, amphibian populations and turtle populations, by the way. Turtles aren't amphibians, are they? No, they're reptiles. So amphibians and reptiles are in steep decline, right? And so we wanted to know if there was a connection between these two things. We also knew that frogs get a lot of gas and liquid transport across their skin. So if acidity perhaps compromised their skin barrier, that could be leading to their decline. I don't really have time to talk about acid rain, but I will tell you a couple things. Acid rain comes from two main sources. Anybody know? Sulfur. Sulfur in coal burns up as SO2, which ends up as sulfuric acid. So coal burning, not good. Also from your car, your automobile, right? When you burn gasoline in your engine, you're combining it with oxygen and you're sparking it to get a little explosion, and the heat from that explosion drives the crankshaft? Is that what it's called? Yeah. The pistons, but then the crankshaft and drives your wheels. But it turns out that, little known fact, air is 20% oxygen, 80% nitrogen. Well, 78% nitrogen. And when the nitrogen gets burned, it turns into nitrogen oxides, which turn into nitric acid. So we get nitric acid out of our cars, and that's what one of the main things our catalytic converters are for, to try and keep those nitric oxides from getting out of the tailpipe. And we get sulfuric acid from soft coal and a little bit from hard coal as well. So, frog skin. Okay. So here's the experiment that, first of all, I should let you know that what we used in this experiment was something called ion-specific electrodes. And specifically, we wanted to try and measure a calcium-specific electrode, because calcium is really important for keeping cells alive. Most of you have used a pH electrode or heard of a pH electrode. What does a pH electrode measure? Acidity. And what's responsible for acidity? An ion, the smallest ion in the whole periodic table, hydrogen, H+, right? So pH electrode is an ion-specific electrode as well. It's just specific for H+, which is what causes acidity. So we now have other ion-specific electrodes that measure other things like calcium, and that's what we decided to use. So here's the experiment we set up here on the left side, right? So we have our calcium electrode that's sticking in an interior solution, and it's connected to a meter, just like a pH meter, but this one's going to measure the voltage due to calcium. That inside solution, that's supposed to say 0 calcium, and then there's a piece of frog skin on the bottom. So it's an open tube, open on the top and open on the bottom, but on the bottom it's covered with frog skin. And that outside solution has about 1 millimolar calcium. That's a biological definition of high calcium, about 1 millimolar. And then we can add acid and control the acidity of that external solution, and we can see if calcium comes in faster as the pH gets lower as we add more and more acid. And my first two students that studied this, Tracy and Wade, got that plot up there on the upper right, which is at pH 7, the skin looked good. At pH 5, it started to leak a little bit. And at pH 3, it looked like it leaked a lot. All right, great. So I had one student do that. I had another student do it. I took the data to a research conference, and people that were familiar with frog skin and familiar with calcium electrodes said, your data don't look quite right. But I didn't really believe them. So I prepared a manuscript. I sent it off to a journal, and the reviewers said, this looks bogus. They rejected the manuscript. So I had a third student, Katie, do it. And what Katie did was she noticed that there was a certain amount of instability in the electrode reading, and she had to let the whole apparatus warm up for about an hour. And then when she did that at all pHs, we got no change. We even pin-pricked the skin and got no change. And the only way we started to see change was if we razor-slashed the skin. It turned out that the reason for this is that these ion-specific electrodes, and this is my fault, I should have checked the literature on this, they're really only sensitive to millimolar calcium concentrations. And if you're trying to look at calcium go across a membrane one at a time, you need 1,000-fold better sensitivity at least, micromolar, maybe even less. So we made 2 mistakes. What were our 2 mistakes? My mistake was exactly to use the wrong instrument, to use a insufficiently sensitive instrument. And the first 2 students also made a mistake. They used the instrument incorrectly, right? Now, why was I so excited? Why were we so excited about that? Because it's what we expected, right? It's what we predicted, right? And we thought, oh, here's a paper. I can get tenure with this, and my students can go off. And but it turned out to be wrong because it was wishful sciencing, right? And I got a careful student. And by the way, Tracy and Wade did just fine, right? Tracy went to med school. She's a doctor. Wade got a master's in education. He's a high school science teacher. Katie, of course, went off and got a PhD in physical chemistry. and she's a chemist. But so, you know, what we learn from this important lesson is that, you know, science only works if you're dispassionate about it, right? When I did my postdoc, I had an advisor who would tell me to go off and do a certain experiment a certain way, and I would do the experiment, and I would come back with the results, and that particular postdoc didn't, well, parts of it worked out, parts of it didn't. I'm describing the parts that didn't, and I told him exactly how I did the experiment, which is exactly how he told me to do the experiment, and I told him that the results were negative. And he said, well, of course the results are negative. You're not supposed to do the experiment that way. And of course, I didn't tell him that that was the way he told me to do the experiment. But you know, this was a particular kind of scientist who was, you know, wedded to certain models, was expecting certain results, and when he didn't get the results, he was sure, you know, that someone else did the experiment wrong. So that's one way of doing science, and sometimes it works, right? If your gut feeling is really good, and a lot of science is gut feeling. If your gut feeling is really good, then more often than not, you will come up with the right answer and eventually figure out the right way to do it. But that's the minority of scientists, believe me, right? The majority get seduced by results that they expect and don't bother, or you know, don't take the time to critique them, right? So you know, you need to learn how to use your instruments correctly. You need to know the limitations of your instruments. You need to set the experiment up properly. It's really important to have a control, right? What's a control? Well, let's look at the cow jump experiment. Of those 4 points, one of those is the control. What's the control? Yeah, 0 volts. Why? Because it's possible that the cow jumps simply because what? It hits the fence, right? Maybe it's scared. It hits the fence and it jumps, right? So the control is really important. You have to have experimental samples where you're changing something, and then a control sample where you're not, and then look at the difference. And the difference between them, one thing I didn't talk about at all, is error bars, right? That looks like a perfect plot. It's never going to be perfect, right? One day at 25 volts, the cow's going to jump, you know, 0.8 feet. Another day, 1.2 feet, et cetera. So you have to do the experiment multiple times. You have to take an average. You have to estimate a standard deviation. And then you have to make sure that the difference between that point and that point is statistically significant, right? Outside of the range of this uncertainty, this experimental uncertainty, right? So we have to know statistics. We have to organize the experiment so that we have controls and samples. We have to use our apparatus correctly. It's a complicated procedure. I think, okay, oops. So before I get to that, actually no, I will show you this slide. These 2 quotes are quotes that I start every single class that I teach, and I've done this since the 90s. This is not specifically related to the scientific method, but rather to the power of science and how we use the power of science. And in his inimitable method, Roald Hoffmann summed up this whole thing into a single sentence. There are no bad molecules, only evil human beings. So the point of this slide, well, I guess the take-home point is that science can be done poorly, as we just talked about, wishful sciencing, Pride and Prejudice in the scientific method, but it can also be used poorly, right? Once science, one of the major goals of much of science is technology, to produce something that's useful. Once that's out there as technology, people, mostly politicians, get to decide how to use that technology. Well, not just politicians. I mean, we use technology in our everyday lives as well. And we get to decide whether we're going to, you know, have our phone on all the time at the dinner table and pay attention to it, or, you know, turn it off when our kids or our grandparents need our attention. So decisions need to be made as well. Okay, so I ended early, which is good. That's more time for music. But I will take some questions about science and the scientific method. Yeah. Oh, we're getting the mic for the questions.
You use the term gut feeling. I wonder if that's the same as what Einstein called intuition. Einstein said that would learn all kinds of things from other scientists, and it'd be boiling around inside his head. And sometime maybe during the night, it'd all come together, and the answer would pop out. That's a method?
You know, we have brains that do work in two different ways, right? We can collect data and we can think logically about the connection between the dependent variable and the independent variable, and we can sort of deduce links. It's called inductive reasoning. But intuition, gut feeling, it's also a big part of what we do. I mean, and by the way, there is evidence, this is tangentially related to your question, that you learn best when you learn for a set period of time, no longer than about 2 hours, and then you sleep. There are a lot of connections that get made between what you went through during the day that happen in your sleep. And that's part of intuition as well. And then I'll just tell you, you know, the famous chemical example of that is Kekulé, who was studying benzene and trying to figure out the structure of benzene, which is a ring, right, with 3 double bonds. And nobody knew about rings in those days. They just knew about straight chain molecules. And he went to bed one night. You know, he worked on it for months and months and couldn't figure out his data. He went to bed one night and he dreamed about a snake biting its tail. And then he woke up and he said, it's a ring. He never would have come up with that without that dream. So is it a method? No. Is it reliable all the time? No, but it's also, in some cases, the best we have. Yeah.
Hi, this is Solveig. Can you hear? I'm a little troubled by one aspect of your throwing a ball at me and we determining. It doesn't make a difference if I'm the Incredible Hulk or a 6-year-old girl. I mean, there's pain threshold, but
yes.
That didn't come into it.
Yes, and that's one of the ways to set the experiment up. But the thing is that, in a sense, it does make a difference in terms of where you are on absolute scale on that pain, but it doesn't make a difference with each individual person.
Right, because it's
right?
subjective, isn't it? So how do you
Right, but that's the point. So I can put a small girl on a scale and throw balls at her, and her pain is still going to be linearly proportional to the mass and the velocity of the ball. Her data will just be offset up compared to the data of the Incredible Hulk. It's still going to be linear, but it'll be offset. Yeah? So each individual can give me a good set of data. So we'll take maybe 2 more.
How about fitting new research into existing research?
So that's very important. And it happens in a number of ways. So when sometimes there are a lot of reasons why certain topics fall out of favor. Maybe we don't yet have the instruments to disprove it yet. And so a certain theory gets accepted, like dark energy, for example, or cold fusion, right? And then suddenly we develop a new technique that we just didn't have 10 years ago or 50 years ago. And now we can come back to this old question, and we can either corroborate that old theory or disprove that old theory, which happens quite often. So, but it is very important to go to the literature, like I didn't do with my calcium electrodes, for example, to go to the literature, figure out what we already know, and define your problem as some wrinkle that we haven't yet solved. Yeah, very important. So all scientists stand on the shoulders of other scientists who have published before them. Yeah. Okay, now we'll take
This is Charlene.
2 more.
I want to go back to the balls and,
Yeah.
and hitting. Do you take into account the fact that each time you hit somebody, it's going to get sorer and sorer in that spot?
Okay, so that would be a bad design, experimental design. Yes, right. So I would have to, if I was really this was like a simplistic experiment. I was pretending you were in 3rd grade, and you're not. So, yeah. So if I really wanted to do that experiment, you probably wouldn't be able to hit the same spot a lot, or maybe you'd have some kind of force detector that didn't get bruised, that kind of thing. That would be a better experimental design, yeah. Yeah, one more.
Could you talk a little bit about how the scientific method may or may not be affected by the sort of mass scale that scientific research is taking place now? Because what you describe is sort of an individual enterprise, and much scientific research.
Yeah. So he's asking how is the scientific method and science in general affected by the fact that we now do experiments differently, right? Like now here at Willamette, I have 1 or 3 or 4 students at a time, and maybe I only have 1 student working on a project, or at most 2. So the kinds of experiments that we do are going to be very different from the kinds of experiments they can do at U of O, where they have large computers, they communicate with people across the world, they have huge data sets that come from blood samples that are drawn all across the world. So there are different kinds of science. And by the way, I didn't mean to imply that all science is done by the scientific method. So I'm sorry if I did that. Some scientists just make new stuff, right? They said, well, scientist X made this molecule by doing this experiment, and I can make a slightly different molecule, and now maybe instead of a toxin, it'll be a drug. There's not always much scientific method involved in that. So it's based more on prediction and hunches sometimes than the scientific method. So the scientific method was very important from 1750, I would say, until the early 1900s. And since then, we do have different kinds of experiments that don't really all use this canonical mathematical law hypothesis testing. Yeah. Okay, so we're going to take about a 4-minute break.